Professor Mr. K. Balraj is working as a polymer consultant and teaching fellow in the area of polymer science and engineering at CEG Anna University, Chennai. He has completed AMIE in Electrical Engineering at the Institution of Engineers India, Calcutta and MTech Polymer Science and Engineering at CEG Anna University. He is also pursuing his doctoral research work in polymer technology. His area of specialization includes polymer rheology, polymer processing, characterization and testing of polymers, polymer blends and composites and insulation technology. He has in-depth experience on plastic properties, testing methods and the relevant standards. He has more than 15 years of teaching experience in polymer science and engineering, including instrumentation in polymer industries, engineering plastics, conducting polymers and rubber technology at CEG Anna University. He has guided more than 30 MTech students in their research projects. He has presented more than 20 research papers in the national and international conferences in the area of polymer science. He has published 10 research papers in the peer-reviewed journals.
Welcome to UGC lecture series in polymer science. In today's class, we will discuss about polymer rheology. What is meant by polymer rheology? What is meant by polymer? Poly means many and mer means single. And mer here refers to what we call it as monomer. When the number of monomers were joined together, the process is what we mean by polymerization. We get a polymer. All the important properties of polymers are due to this. And rheology means science of deformation and flow. And in the polymer, why these polymeric materials are of relevance in all the developed countries as well as the developing countries. The main reason being the superior properties compared to the conventional materials. In today's world, you could see anything from day to day to aircrafts or in radars, wherever you go, where high performance materials where like iron is used or completely replaced by polymers. The simple reason being that the way these mer or one unit is joined together, what we call it as a polymer. That is why it is gaining importance. Now, the polymer rheology in this, how these materials are converted into useful form. For example, like a chair, a plastic chair, or to a aircraft wing. In all these, the rheology plays the main role, which simply means the science of deformation and flow. In this class, we will see the relevance of rheology with respect to polymer, and then what is meant by viscosity and how viscosity and polymer processing are related. Introduction. Flow process in manufacturing a polymer products or in general in any product. So, this is a typical scheme starting from the raw material to the processing and then to the final product. So, in the processing is where the rheology comes, and then the equipment design. What is meant by rheology is a Greek term which means science of deformation and flow. In polymers, when you heat a conventional material, it straight away undergoes phase transformation, for example, a solid to a liquid, whereas a polymer, it never becomes a liquid unless you heat it to a very high temperature of some 1000 degrees Celsius or so. So, in the process, it tries to deform. Why it is trying to deform means later on we will see a term called entanglement. In a given polymer sample, you will have umpteen number of chains, each chain with a different length. Here the length directly corresponds to the number of units that has been joined together in a single chain. As a result, these polymeric chains gets entangled, and because of this it will not flow readily when you melt it, and then when you try to pass through a injection mold, it will not readily flow. It will first deform. So, that is where the rheology is important. So, the rheological studies are much essential for good processing of a polymeric material into a final product. So, here the transformation means deformation into a specified shape. And then where this is significant, in a, for example, in a extrusion molding machine, if you look into it, has a different zones like feed zone, mid-ring zone and processing zone. The feed zone is where you drop these pellets. Mostly in the polymeric materials are available in the form of either a powder or pellet, and it fed into a feed zone. The mid-ring zone is where these pellets or powders tries to get a viscous form. So, that is where this rheology is important, that is the first section of the melt flow. And also the rheological studies will give an information how these polymers will behave during actual polymer processing. Before we go for processing itself, from these rheological curves like your its velocity gradient, later on we will see the rheological properties are simply understood by with respect to a plot between shear stress versus shear rate. So, the shear rate is important. What is the rate at which these viscous liquids are sheared either in a extrusion molding machine or in a blow molding machine. So, that is where the rheological studies helps. And in this, for example, the effect of temperature is of course very important. All the material like other materials, polymeric materials do the viscosity drops when you increase the temperature, it viscosity drops, and pressure almost has no little effect compared to the conventional materials, and of course geometry. So, why these polymeric materials are more significant nowadays means more intricate shapes are possible, starting from a hairpin to a very complex for example, a IC board. So, whatever the complex form, a polymeric material can be converted into complex form. So, therefore, the geometry of this is also important. Apart from extrusion and injection molding, you have other processes as well, like compression molding, blow molding, where you get your PET bottles, calendering, where you get your all your adhesive tapes, and of course cold forming and spinning of fiber. Sometimes these polymers are converted into a fiber form, and then later on it is mixed with a polymer, and then they prepare a composite, which is what is used in aircrafts. For many simple fluids, the study of rheology means measurement of viscosity, because viscosity and rheology are the terms which goes hand in hand. Now, the viscosity depends on temperature of course, and as well as pressure, and the rheology of polymers is much more complex compared to the other fluids because of its non-ideal behavior. Non-ideal behavior in the sense there is no linear relationship between its velocity gradient and the pressure. All these rheological properties do depend on the, as I told already, in the shear rate. We will see what is meant by the shear rate, how the viscous liquids are getting sheared inside a processing machine. Of course, the molecular weight is more important, the structure of polymers, whether it has bulky groups present in as a side chain, and then the of course concentration of additives. Additives here refers to all the coloring agents, pigments for aesthetic appearance, and the flow behavior is required in the processing and fabrication of plastics, and degree of orientation. The degree of orientation here refers to the polymeric chains, the entangled polymeric chains. When it is subject to high temperature and then it is subject to shear, it get oriented in a particular direction, which facilitates more easy flow. And molecular orientation do have a effect on the mechanical properties. If it is oriented in the drawn direction, the temperature, its mechanical properties are very high compared to the transverse direction. Of course, the mechanical properties are the most important properties required for any polymeric products. In actual conditions, the optimum mechanical properties is not important, that is a very high tensile strength or a very high compressive strength material is of course desirable, but at the same time how well it could be processed. The processing equipment design should be fast or simple, and it should be at an affordable cost. So, that is the actual reality with respect to polymeric processing. Now, let us see some of the importance of these rheological studies. In the rheological studies, the flow behavior of polymeric melts, as the polymeric pellets are melted and then it is allowed to flow as a viscous liquid. How well it flows, its flow behavior, as we have seen earlier, it is not ideal behavior, it is a non-ideal behavior. There is a non-ideal relationship between its velocity gradient as well as its applied stress. It has become more complex. So, the behavior of flow during flowing along with the other factors that influences the flow of polymers, and then final properties, of course, the final properties of the polymer, qualitative and quantitative parameters such as the output. For example, in a given hour, if you want to prepare a plastic chair, number of chairs per hour. So, such a qualitative as well as quantitative as well as qualitative data could be obtained from these rheological studies. Importance of rheological studies. So, one can choose the suitable polymer for specific processing conditions and services, that is to produce a product with optimum processing properties, and importance in real processing to produce maximum output with minimum input. So, these are all the synergical effect what we try to achieve. In the sense in the modern world, like today, earlier most people are familiar with either polyethylene or PVC and of course PET bottles, and now today you could see easily around 200 or more engineering plastics that have been prepared commercially and marketed. As a result, with the help of these rheological studies, one can choose a suitable polymer for a given type of product and for a given type of process as well. In some cases, the factors such as molecular structure, morphology, polymer melt, blends and polymer fortification can be studied by finding the relationship between the rheological properties and material structure. So, in the molecular structure, how well the molecules are distributed, like narrow molecular weight distribution or a wide molecular weight distribution, and the morphology here refers to whether the polymeric material is a amorphous material or a crystalline material, and polymer melt, generally the crystalline materials has a very high melt temperature. When no suitable one polymer alone is suitable for a given type of process or a specific product, then we go for a polymer blend, wherein you choose two different polymers and then you try to go for a blend. So, that is all these could be done with the help of these rheological studies. Next, we will see viscosity. Viscosity is resistance to flow. In simple terms, most people do find it difficult to understand what is by viscosity. It is as simple, you compare flow of honey as well as any waterfall. So, the flow of honey, it little bit takes more time. When you try to transfer a bottle of honey into a glass tumbler or so, you will find it very difficult. The honey finds very difficult to flow, which simply means it is a very high viscous, whereas water will readily flow. So, that is how one can understand viscosity. So, in the plastic material, viscosity is more important, because when a polymeric material is melted, its flow behavior is more dynamic, and also it depends on so many other factors as well. Therefore, viscosity is more relevant to plastics or polymers. The characteristic of how the material flow in general is a very good indication of the molecular weight as well as other factors. If the molecular weight is very high, then the material finds difficult to flow easily, and the molecular weight is very low, then it can flow very easily. The other factors include the consistency of additives and the filler amounts and the degree of branching. So, the degree of branching refers to the morphological structure. More branching generally reduces the tendency of the polymeric melts to flow easily. For these reasons, rheology or the study of flow is very important to maintain this consistency in plastic materials. In simple terms, it is simply the resistance to flow, and it has a direct effect on how the material flows. Now, let us see with an example. Consider two plates. One is given a velocity in the positive x direction, it can move. The top plate 1, the marked as 1, can move because of the applied velocity, and then the bottom plate marked as 3 is stationary. Now, let us consider a viscous liquid that is simply kept in between these two plates. Now, if the top plate is pulled in this right side direction as indicated in the arrow mark, and then you could see the displacement of these liquids, which is the shaded region is the its original position. Now, you could find it has moved tilted slightly, but not as a whole, rather it follows a specific way, like this is one layer, and this is another layer, this is another layer, this is another layer, or in other words, the liquid that is present between these two plates are subject to a shear, and then this shear effect is getting transferred in the layered fashion, and then this resistance offered by this liquid is what we call it as viscosity, and these are the terminologies associated with that. That the applied velocity to the top plate, we can call it as a shear stress, or which is simply the shear force per unit area, and then the shear strain is the displacement by its original distance, and then the viscosity is simply the ratio between these two, the applied stress versus the given strain. And then with respect to viscosity, from the literature one could find all the viscosity data are available in centipoise. So, what is 1 centipoise means, which is simply 1 millipascal second. Unit for shear stress Newton per meter squared, and unit for strain is simply the second. So, therefore, 1 Newton per meter squared is 1 Pascal. Therefore, 1 Pascal second is the unit for viscosity in SI system, and in CGS system it is given in centipoise. So, therefore, most of the literature data are always in centipoise. Even today viscosity data are given in centipoise. So, 1 centipoise is roughly equal to 1 millipascal second, and the viscosity decreases rapidly as temperature increases, like all other conventional materials. And then ideal fluids, here ideal fluids refers to the fluids which have a linear relationship between the shear stress and the shear strain. Such fluids are called as Newtonian fluids. In Newtonian fluids, the viscosity is independent of the rate of shear, and shear rate is a measure of rate of shear deformation. Let us see a typical rheogram for Newtonian fluids is shown here. One is for high viscosity, another one is for low viscosity. In both the cases, you could find there is a linear relationship between the shear stress as well as the shear rate. Such liquids are called Newtonian liquids. There are other category which comes under non-Newtonian behavior, as shown here, where relationship between shear stress as well as the shear rate is not linear like in a Newtonian fluid, whereas it goes in different fashion. And then there are two common fluid which is named as pseudoplastic and dilatant, which is more common in polymeric systems. Most of the polymeric materials and rubber compounds do behave as a pseudoplastic, and then how this pseudoplastic is related to the pseudoplastic behavior is related to the morphology of polymer is simple. The morphology polymer, any polymer has long chain, and these long chains are coiled and are more complex structures. That is the reason for the pseudoplastic behavior. And with respect to dilatant fluid, with the increase in shear rate, the viscosity will increase. Therefore, for dilatant system it will have more processing difficulties. And another category is thixotrophy. It is again another non-Newtonian type pseudoplastic fluids. It is similar to pseudoplastic fluids, except that there is a time dependent change in viscosity. The viscosity not depends on shear rate alone, it also depends on the time, how much time the polymeric melt or the liquid is subjected to shear rate. And then viscosity in some cases decreases as the material is stirred until some minimum value is reached. It is again increases when the substance is no longer agitated. So, therefore, stirring do have an effect on the viscosity. A typical thixotropic substances at different shear rates, you could see all has depends on time, and many gels and colloids like your toothpaste are examples of thixotropic material, which will be in stable form at rest, but become fluid when it is agitated. Now, with respect to viscosity, there are a number of terms to describe viscosity like constant viscosity, apparent viscosity. All these viscosity data are derived from the shear stress versus shear rate curve. For example, in this shear stress versus shear rate rheogram, you could see different viscosities marked. The neta O, which is obtained from the initial part of the stress strain curve, which is the viscosity data for Newtonian fluids, and then you have a constant viscosity which is determined at a particular place, and then the apparent viscosity, the viscosity from the origin to a specified point. So, these are the different viscosity data that are available for the rheological studies. From viscosity, we will move on to polymer processing. So, in the polymer processing, main thing is the conversion of these polymeric powders or pellets into a fluid. So, that means when it melts, then the viscosity comes into picture. The general characteristics of polymeric materials is that it will have high viscosity. A typical melt viscosity values are given for comparison: water 10 power minus 3, olive oil 10 power minus 1, and pitch, which is the coal tar 10 power 9, and then in this you could find the polymeric melts from 100 to 1 lakh or so. So, that is a typical melt viscosity range all the commercially available polymeric materials do fit in. In general, viscosity decreases with increasing shear rate. When you increase the shear rate, viscosity decreases. Most of the polymers do exhibit such behavior. Such polymers are pseudoplastic. Actual form of the flow curve, the flow curve here refers to the rheogram, depends on the type of polymer, molecular weight as we have discussed earlier, and then molecular weight distribution, whether it is widely distributed or narrowly distributed, and degree of branching. And then there are few exceptions from pseudoplastic, which comes into the dilatant system. So, the dilatant behavior simply means that when you increase the shear rate, the viscosity increases. So, therefore, dilatant polymeric systems are not commercially significant. And then the next one is the shear rate. The large variations in the shear rate which exist in manufacturing process are shown below. For example, for compression molding it is 1 to 10, calendering 10 to 10 power 3 there. So, with respect to the type of processing operation, the shear rate varies, hence again it is going to affect the viscosity. To conclude, with respect to viscosity, the two main parameters for viscosity is, one is temperature, another one is shear rate. As the temperature increases, definitely the viscosity will come down. As a result, the polymeric flow behavior is more easy, and this is because all the entangled chains are loosened up, and then they simply slide one over the another. As a result, the flow is more easy. And with respect to the shear rate, as you increase the shear rate, the polymer chains orient in the direction of flow, and again it also facilitates more easy flow. Because of the high aspect ratio here is simply the length versus diameter. For example, a typical polymer of molecular weight 1 lakh, then it will have 1 lakh units, roughly 1 lakh meter or so, whereas the diameter will be of in the nanoscale. As a result, the high aspect ratio of this polymeric system do have a effect when it is in the molten state. This is what we call it as entanglement. The entanglement of the polymer chain causes them to have very high viscosity. Understanding how temperature affects the viscosity should not be difficult. That is, as the material is heated, they expand like the other conventional materials. As you heat, they expand. So, the molecules are more free. Therefore, temperature versus viscosity is more easily understandable compared to the shear rate. We will see why. Because to understand the shear rate, few more topics are important, which are what is meant by Reynolds number, what is laminar flow, what is turbulent flow, and these Newtonian or non-Newtonian fluids are again based you have Newtonian fluid and non-Newtonian fluid. This classification itself is based on Reynolds number. What is Reynolds number? The Reynolds number, it is a dimensionless number which is given by rho v d by mu if it is a pipe flow. Here d refers to diameter if it is a pipe. If it is over a flat plate, then we go for L. And then this Reynolds number value less than 2300 laminar flow, greater than 4000 turbulent flow. In between is what we call it as transitional flow. And then in laminar and turbulent flow, the turbulent flow provides a very high degree of mixing, which again is useful in certain applications where you want a better heat transfer. Whereas the laminar flow, as is shown in the diagram, the layer that is just below the surface of the pipe, there is more frictional drag. As a result, it will not flow easily, whereas in the center of the pipe there is very less drag, and then it could move very fastly. Such a pattern like this is what we call it as laminar flow. Let me summarize today's class what we have discussed about polymer rheology. Of course, the first thing is viscosity. What is meant by viscosity? How viscosity of polymer is different from other conventional materials, and what is rheology, and how rheology of polymeric systems is more important when it comes to conversion of any polymeric material into a final product, and then how the polymer processing depends on both viscosity as well as rheology. These are the questions the viewers should think over after viewing this class. What is meant by viscosity, what is meant by rheology, and what is the significance of viscosity with respect to polymer processing. Thank you.